What would it feel like to fall into the densest object in the universe, besides a black hole? To approach something so massive that a teaspoon of its matter weighs more than Mount Everest, compressed into a sphere no wider than a city. Tonight, we explore one of the cosmos's most extreme thought experiments. We'll descend toward a neutron star, feeling every impossible force, witnessing every relativistic effect, understanding every stage of an encounter that would last mere seconds but reveal eternal truths about the nature of matter, gravity, and time itself. This is not a journey anyone could survive, but it is a journey worth taking in the safety of imagination, here in the quiet darkness, as your breathing slows and your thoughts begin to drift among the stardust. Over the next hour and a half, we'll approach this cosmic lighthouse from a safe distance, then begin our fall. We'll feel the acceleration build, experience time itself bending around us, and witness the spectacular death that awaits anything brave or foolish enough to meet a neutron star face to face. The science will be real, the physics will be accurate, but the narration will be gentle, painted in soft words and careful pauses, designed to let your mind wander through the cosmos, while your body finds the rest it needs. There are no tests at the end of this journey, no need to remember every detail. This is simply an invitation to wonder at the extreme edges of physics, to contemplate forces beyond human comprehension, and to let those thoughts carry you peacefully towards sleep. So find your comfortable place, let your shoulders soften. Close your eyes if you wish. The neutron star awaits, spinning in the darkness, pulling at space-time itself, patient and terrible and beautiful beyond words. Let's begin our descent. Before we fall, we should understand what we're falling toward. Neutron stars are the compressed cores of massive stars, stars that once burned bright and hot, fusing hydrogen into helium, helium into carbon, carbon into heavier elements, climbing the ladder of nuclear fusion until their cores filled with iron. And there, at iron, the fusion process stops. Iron takes more energy to fuse than it releases. The core becomes a dead thing, no longer pushing outward against gravity's inward crush, and so the core collapses. In less than a second, a stellar core larger than Earth compresses down to a sphere barely 20 kilometers across. The collapse happens so fast, so violently, that it rebounds, sending the star's outer layers, exploding outward in a supernova, one of the brightest events in the universe. For a few weeks, that dying star can outshine an entire galaxy. But at the center, hidden behind the expanding debris cloud, something remarkable emerges from the violence. A neutron star. Imagine taking the entire mass of our sun, every bit of the plasma that makes up that enormous ball of fusion fire, all 2,000 trillion kilograms of it, and crushing it down until it fits inside a city. Not a large city, a medium city. Philadelphia, perhaps, or Seattle. The density becomes incomprehensible. A single teaspoon of neutron star material, just 5 milliliters, the amount you might use to stir your coffee, would weigh somewhere between 1 and 6 billion tons on Earth. Estimates vary, but most calculations suggest it's comparable to the mass of all humanity combined, or even Mount Everest itself, condensed into something you could hold in your palm, if your palm could somehow avoid being obliterated by its gravity. This density is achieved because the collapse doesn't stop at white dwarf levels, where electron degeneracy pressure holds things up. The pressure becomes so extreme that electrons get pushed into protons, combining to form neutrons through a process called electron capture. The star becomes, essentially, one giant atomic nucleus, made almost entirely of neutrons, packed together as tightly as matter can be packed without collapsing further into a black hole. The density at a neutron star's core reaches approximately 4 times 10 to the 17th kilograms per cubic meter, roughly the density of an atomic nucleus itself, or about 280 trillion grams per cubic centimeter. At these densities, normal atomic structure ceases to exist. On Earth, atoms are mostly empty space. If an atom were the size of a football stadium, the nucleus would be a pea at the center, and the electrons would be tiny specks orbiting in the upper stands. All that space in between, empty, or rather, filled with electromagnetic fields that keep electrons from collapsing into the nucleus. But in a neutron star, that space is gone. The neutrons are pressed together, touching, crushed against each other with such force that they resist further compression only through neutron degeneracy pressure, a quantum mechanical effect where particles of the same type refuse to occupy the same quantum state. It's the same principle that keeps white dwarfs from collapsing, but operating one level deeper in the structure of matter. The surface of a neutron star is no less strange. It's believed to be crystalline, a solid crust of atomic nuclei arranged in a lattice, something like a crystal, but one made of iron and other heavy elements, crushed to densities millions of times greater than anything on Earth. This crust is extraordinarily smooth. The gravity is so intense that any irregularity, any mountain or bump larger than a fraction of a millimeter, would be pulled flat almost instantly. Recent calculations suggest that the maximum height of any mountain on a neutron star's surface would be less than 1/10 of a millimeter, essentially perfectly smooth by any standard we can comprehend. Beneath this crust lies the outer core, where free neutrons flow like a superfluid, a quantum liquid with zero viscosity, able to flow without friction, defying the normal rules of fluid dynamics. Deeper still, in the inner core, conditions become so extreme that physicists are not entirely sure what exists there. Perhaps neutrons break down into quarks, forming quark matter. Perhaps strange matter appears, a hypothetical form of matter made of up, down, and strange quarks. Perhaps something even more exotic emerges, some state of matter that can only exist under pressures that exceed those in any atomic nucleus. Between the crust and the core lies one of nature's strangest inventions, a transition zone where matter arranges itself into structures nicknamed nuclear pasta. This name, whimsical as it sounds, describes real physical structures that form when matter exists at densities around 1 trillion grams per cubic centimeter. At these extraordinary pressures, atomic nuclei can no longer maintain their spherical shapes. The intense gravitational compression forces them into elongated, distorted forms that would be impossible anywhere else in the universe. The arrangement depends on the precise density at each layer, creating a hierarchy of exotic structures as we descend through the inner crust. At the lower densities of this pasta zone, around 10 to the 12th grams per cubic centimeter, the nuclei cluster into shapes resembling meatballs, roughly spherical but distorted, each containing perhaps 40 to 50 protons and a similar number of neutrons, separated by a sea of free neutrons that have dripped out of the lattice structure above. These, nuclei, float in the neutron fluid, still discrete entities, but beginning to feel the pressure of their neighbors. As we descend deeper and the density climbs, these spheres can no longer maintain separation. They merge and stretch, deforming into long cylinders of nuclear matter, structures genuinely resembling spaghetti strands threading through the neutron sea. Each strand might be only femtometers wide, smaller than an atomic nucleus would be in normal matter, but extends for relatively vast distances in the context of nuclear scales. Push deeper still, and the strands flatten and merge. The matter reorganizes into sheets, parallel layers of nuclear material stacked like cosmic lasagna. Each sheet is perhaps a femtometer thick, separated by layers of neutron matter. The geometry has shifted from individual objects to continuous planes, a fundamental change in how matter structures itself. And then, in a reversal that seems almost whimsical, the pattern inverts. As density continues to increase toward the core, the sheets develop holes. Instead of sheets of nuclei separated by neutron matter, we now have sheets of neutron matter perforated by tubes of clustered nucleons, anti-lasagna, if you will. The holes organize themselves into cylindrical voids, creating an anti-spaghetti phase where the neutron sea is threaded through with hollow passages of denser material. Finally, near the transition to the outer core, these tubes fragment and pinch off, creating spherical bubbles, pockets of neutron, rich matter embedded in a matrix of heavier nuclei. This Swiss cheese structure, or anti-meatballs phase, represents the last gasp of nuclear structure before matter gives up entirely and becomes a uniform soup of neutrons. This pasta layer may occupy only a kilometer or two of the neutron star's radius, a narrow transition zone between the solid crust and the liquid core. But its existence reveals something profound about the nature of matter under extreme conditions. Even when squeezed to densities that obliterate normal atomic structure, matter still finds ways to organize, to create patterns, to resist the absolute uniformity that pure compression might seem to demand. The forces at work here: gravity trying to compress everything into formless uniformity, nuclear forces trying to maintain some structure, quantum mechanical principles imposing their own constraints, create a delicate balance that manifests as these exotic geometries. The pasta phases represent matter at the very edge of what can exist, while still maintaining any kind of internal structure. Beyond this layer, in the outer core, the density reaches values equal to or exceeding the density inside atomic nuclear on Earth. At these densities, somewhere around 280 trillion grams per cubic centimeter, the distinction between individual particles begins to blur. The neutrons pack so tightly that they overlap, flowing as a superfluid, a quantum liquid with zero viscosity, able to flow without friction, defying every intuition we've developed about how fluids should behave. Within this superfluid, a small percentage of protons persist, perhaps 5 to 10% of the particles, along with electrons to maintain charge neutrality. These protons may themselves form a superconductor, carrying electrical current with zero resistance, creating persistent current loops that could contribute to the neutron star's magnetic field. And then, at the boundary where the neutron star's density reaches twice or even 3 times that of an atomic nucleus, we cross into territory where our understanding falters entirely. We don't know what exists in the innermost core. Perhaps the neutrons themselves break down. Under sufficient pressure, the quarks that compose them, the up and down quarks bound together by the strong force, might deconfine, spilling out of their neutron containers to form a quark-gluon plasma, a state of matter that last existed in the universe a fraction of a second after the Big Bang. Perhaps strange quarks appear. In normal matter, strange quarks are unstable, decaying almost instantly into lighter quarks. But at neutron star core densities, it might become energetically favorable for strange quarks to exist, forming strange matter. A hypothetical phase where up, down, and strange quarks mingle freely. Some theories suggest this strange matter might actually be more stable than normal matter, raising the unsettling possibility that neutron stars could be, in their cores, strange stars. Perhaps even more exotic phases emerge, pion condensates, where force-carrying particles called pions form a quantum condensate, condensates, involving even stranger particles, hyperons, baryons containing strange quarks that are heavier cousins of protons and neutrons. Each of these possibilities emerges from different theories, different assumptions about how quantum chromodynamics, the theory governing the strong nuclear force, behaves at these impossible densities. We can't know for certain. We can't replicate these conditions in laboratories. The most powerful particle accelerators on Earth can't approach these densities, can't sustain these pressures, can't probe these states of matter directly. The best we can do is observe neutron stars from afar, measure their masses and radii with increasing precision, detect the gravitational waves they emit when they collide, and let those observations constrain our theories. We watch these cosmic laboratories from a safe distance, reading the signatures of physics that we cannot yet fully comprehend. But we do know this neutron stars are as close as nature comes to the edge. Any more mass, any more compression, and they would collapse past the point of no return, crushed beyond even neutron degeneracy pressure, becoming black holes. They exist in that narrow band between white dwarfs and event horizons, balanced on a knife, edge of physics, held up by quantum mechanical principles operating at their absolute limits. And they spin. Oh, how they spin! When the core of a massive star collapses, it conserves angular momentum. The star was rotating before, slowly, majestically. But as it shrinks, the rotation speeds up dramatically. The same way an ice skater spins faster when they pull their arms inward. Neutron stars can rotate hundreds of times per second when they're first born, their surfaces moving at a significant fraction of the speed of light. The fastest spinning neutron star we've discovered rotates 716 times every second. That's faster than the blades of a kitchen blender. An object with more mass than the Sun, spinning so fast that a point on its equator is moving at about 24% of light speed. And they're magnetic, unimaginably magnetic. The collapse that forms a neutron star doesn't just compress mass, it compresses magnetic field lines. A star that might have had a magnetic field similar to the Sun's gets that field crushed down into a sphere 20 kilometers across. The field strength increases by factors of trillions. A typical young neutron star has a magnetic field of about 1 trillion Gauss. That's about 1 trillion times stronger than Earth's magnetic field. It's strong enough to pull the iron from your blood from thousands of kilometers away. It's strong enough to disrupt atomic bonds, to stretch atoms into needle-like shapes aligned with the field. And then there are magnetars, neutron stars with even more powerful magnetic fields, reaching 1,000 trillion Gauss or more. In these fields, even the vacuum of space becomes polarized. Photons split in two. The very structure of empty space gets distorted by the magnetic energy density. These are the objects we're contemplating, these lighthouses in the cosmic dark, these impossible densities, these spinning, magnetic, gravitational monsters that pack the fury of a supernova into a ball the size of a city. This is what waits for us at the end of our fall. Let's begin somewhere safe. 1 million kilometers away from the neutron star, about 2.5 times the distance between Earth and the Moon. Far enough that its gravity is noticeable, but not yet dangerous. Far enough that we can observe, contemplate, prepare ourselves for what comes next. From here, the neutron star might not look like much. It's small, so small that even though it contains more mass than the Sun, it appears as barely more than a point of light. Young neutron stars have surface temperatures of around 1,000,000 Kelvin, hot enough to glow blue, white, radiating most of their energy in ultraviolet and X rays rather than visible light. An older one might be dimmer, cooled to a few 100,000 Kelvin, still hotter than any normal star's surface, but faint because of its tiny size. But you would feel it. Oh, you would feel it. Even from 1,000,000 kilometers away, the gravitational pull would be noticeable. Not overwhelming, not yet, but present in a way that Earth's gravity never is. Your weight would be perhaps twice what you're used to. Uncomfortable, but manageable. You could still move, still function, though every motion would require more effort. Every breath would feel slightly harder to draw. And if this were a pulsar, a neutron star whose magnetic poles are misaligned with its rotation axis, sweeping beams of radiation across space like a cosmic lighthouse. You would see it flash, on, off, on, off. If it's rotating once per second, you'd see a rhythmic pulse, steady as a metronome, regular as a heartbeat, each flash announcing that somewhere in the cosmos, a city-sized sphere of impossible density has completed another rotation. Some pulsars flash hundreds of times per second, their surfaces moving at significant fractions of light speed, their magnetic fields generating beams so intense they can be detected across thousands of light years. The fastest we've found rotates 716 times every second. A blur of motion, a star-sized object spinning faster than any human-made machine could ever approach, driven by angular momentum conserved from the collapse of a sun. These pulses are so regular, so precise, that they're among the most accurate clocks in the universe. We've measured pulsars that keep time more accurately than atomic clocks on Earth. Their periods can be known to within a billionth of a second, stable over decades. Early radio astronomers who first detected these signals briefly wondered if they might be artificial. So perfect was their timing, so regular their rhythm. We joke now about those early speculations. Little green men sending signals across the cosmos. But there's something almost alive about a pulsar's steadiness. Something that suggests intention, even though we know it's just physics. Just the conservation of angular momentum. Just a lighthouse rotating in the dark. And yet they're slowing down. Every single one of them. Every rotation takes a tiny bit more time than the last. The spinning magnetic field acts as a brake, radiating energy into space in the form of electromagnetic waves and relativistic particles, gradually stealing angular momentum from the star. The process is glacially slow by human standards. A pulsar spinning once per second might slow to once every 2 seconds over 30 million years. But it's inexorable, unstoppable, written into the physics of rotating magnetic fields. Give a young pulsar a few billion years, and it will slow from hundreds of rotations per second to once every few seconds, then to once every tens of seconds, eventually falling silent as its rotation drops below the threshold needed to generate detectable pulses. It will still spin, still exist, but it will no longer light up our radio telescopes, no longer announce its presence to the cosmos. It will fade into the darkness, one more invisible remnant of stellar death. But for now, from our safe distance, this one spins and flashes, a beacon in the darkness, and it pulls. The gravitational influence reaches out, gentle but insistent, tugging at spacetime itself. Even from 1,000,000 kilometers, the fabric of reality is slightly warped by the neutron star's presence. Not much, not enough to notice without sensitive instruments, but enough to be real, enough to be measurable. Light passing near the neutron star bends, following the curved spacetime created by its mass. Time flows slightly differently here than it does far from any gravitational source. Not noticeably slower yet, but measurably so. Clocks at this distance would tick ever so slightly behind clocks in flat space, losing perhaps microseconds per day. And if you were to release an object, say, a coin, it would fall. Not straight down, because down has no meaning in space, but toward the neutron star. Slowly at first, accelerating gradually under that doubled gravity. You could watch it drift away, tumbling in the vacuum, catching and reflecting the pulsar's flashes as it spirals inward. You could, theoretically, stay here for a long time, with sufficient propulsion to counter the gravitational pull. You could orbit at this distance, studying the neutron star from relative safety. This is where observation satellites might position themselves, far enough to survive, but close enough to gather data. From here, you could measure the star's temperature by analyzing its thermal radiation, track its rotation by timing the pulses, map its magnetic field by watching how it accelerates particles. You could spend years here, decades even, slowly compiling the data that would help humanity understand these objects. Many astronomers dream of such observations, of being able to study a neutron star up close, of seeing with human eyes what we've only glimpsed through telescopes and equations. But we're not here to observe safely from a distance. We're here to fall. Time itself runs slightly slower here than it does far from any massive object. If we had a clock and could compare it with one floating in empty intergalactic space, far from any star or galaxy, we'd find our clock running just a fraction slower. Not by much at this distance, maybe a few parts per billion, but enough to be real. Light bends here too, ever so slightly. If we could see stars behind the neutron star, we'd notice their positions shifted, displaced by the warping of space-time around the dense core. This is gravitational lensing, the same effect that lets astronomers study distant galaxies by using galaxy clusters as natural telescopes, magnifying and distorting the light from even more distant sources. The magnetic field at this distance is still relatively weak, weaker than a refrigerator magnet, certainly weaker than an MRI machine. But it's there, permeating space, carried by particles streaming away from the star's surface, forming a magnetosphere that extends far into space. If this is a pulsar, that magnetosphere is where the magic happens. Charged particles get accelerated along the magnetic field lines, streaming away from the poles at nearly the speed of light. When they do, they emit radiation, radio waves, visible light, X-rays, gamma rays, depending on the particle's energies and the field's strength. This is the lighthouse beam we see pulsing, sweeping across space as the star rotates. But we're safe here. For now, at this distance, we could still turn around. We could fire our theoretical engines, accelerate away, escape the gravitational well, and return to the gentler cosmos beyond the neutron star's influence. The escape velocity here is high but manageable. Perhaps a few thousand kilometers per second, achievable with enough fuel and time. But we're not going to escape. We're going to fall. So let's take a moment, here in the relative safety of distance, to appreciate what we're about to do. To look inward at our bodies, fragile, chemical, held together by electromagnetic forces that seem strong on human scales, but are nothing compared to what awaits us. To feel the complexity of our biology, the intricate dance of molecules and cells, the electrical signals coursing through neurons, the rhythmic pumping of the heart. All of this, every atom of our being, was forged in stars. The carbon in our cells, the oxygen in our lungs, the iron in our blood, the calcium in our bones. All of it was created in nuclear fusion deep inside stars that lived and died before the sun was born. Some of that material came from supernova, explosions like the one that created the neutron star we're about to fall toward. We are, literally, made of star stuff, and now we're going to return to it in the most extreme way possible. The descent begins. We let go of our theoretical safety. Perhaps we use a gentle push from small thrusters. Perhaps we simply release ourselves from whatever anchor was keeping us in place. However it happens, we start to fall. At first, the change is subtle. Our velocity increases slowly, pulled by the neutron star's gravity, but not yet dramatically accelerated. We're in free fall, weightless from our own perspective, like an astronaut in orbit, though we're not in orbit. We're falling straight down. The neutron star ahead appears to brighten slightly as we approach, not because it's actually getting brighter, but because we're closing the distance, collecting more of its light. The pulses, if this is a pulsar, maintain their rhythm, on-off, on-off, a metronome for the impossible journey ahead, 900,000 kilometers away now. Our velocity is building. We're falling at perhaps a few hundred meters per second, faster than any bullet, faster than the speed of sound on Earth, but still slow by cosmic standards. The gravitational pull strengthens. If we could still feel weight, which we can't, not in free fall, it would be perhaps 3 times Earth's surface gravity, but we don't feel it. In free fall, everything falls together. Every atom of our body accelerates at the same rate. There's no sensation of falling, no feeling of weight. This is Einstein's equivalence principle in action. You cannot distinguish between free fall in a gravitational field and floating in empty space, at least not locally, at least not yet. The not yet is important. 800,000 kilometers. The velocity continues to build. We're falling faster now, accelerating under the neutron star's pull, gaining speed with every passing moment. Several kilometers per second. The stars behind us would start to show Doppler shift. If we looked back, their light blue shifted, compressed to slightly shorter wavelengths by our motion. And here, beginning to stir, comes the first hint of what's to come. Tidal forces. On Earth, we experience tidal forces from the moon and sun, the difference in gravitational pull between the side of Earth facing these bodies and the side facing away. These forces are what cause ocean tides, the rhythmic rise and fall of water levels as Earth rotates. But Earth experiences this across thousands of kilometers. The human body is less than 2 meters tall. For any normal gravitational field, the difference in pull between your head and feet is negligible, unnoticeable. Your body falls as a unit, every part accelerating together, in harmony. But as we approach the neutron star, as the gravitational field becomes stronger and stronger, the difference in pull between parts of our body begins to matter. 700,000 kilometers. The tidal force is still small, but it's there. If we could measure it precisely, we'd find that our feet, slightly closer to the neutron star than our head, are experiencing slightly more gravitational pull. They want to accelerate faster. They want to fall ahead of our head. This difference is measured in fractions of a percent right now, meaningless in practical terms, but it's growing. 600,000 kilometers. We're falling faster and faster, tens of kilometers per second now, a significant fraction of Earth's escape velocity. The neutron star ahead appears larger, brighter. The pulses come with metronomic regularity, each one a reminder that we're falling towards something spinning hundreds of times per second. The magnetic field is getting stronger, still weak by everyday standards, but measurable. If we had a compass, it would start to point toward the neutron star's magnetic poles. If we had sensitive instruments, we'd detect charged particles streaming past us, riding the magnetic field lines away from the star, like surfers on waves of electromagnetic force. And the tidal forces continue to grow, 500,000 kilometers. Now the difference matters, at least mathematically. Our feet are experiencing perhaps 1% more gravitational pull than our head. In free fall, this doesn't hurt, not yet. But it means our body is very slowly being stretched, like a piece of dough being pulled by hands at different speeds. The stretching is so gradual, so gentle, that if we could feel it, it would be like the most delicate massage, a subtle lengthening of every fiber. But we can't feel it. Not yet. We're falling too uniformly, too completely, for the difference to register as discomfort. Time dilation is becoming more noticeable too. Not to us. We wouldn't feel it. Time passes normally from our perspective. But if there were observers far from the neutron star, watching us fall, they would start to notice our clocks running slower than theirs. The difference is still small at this distance. Perhaps 1 part in a million, but it's there, real and measurable. And it's growing. 400,000 kilometers. The acceleration continues. We're falling faster and faster, tens of kilometers per second, accelerating continuously under the neutron star's pull. The stars ahead are noticeably blue, shifted now if we were paying attention to them. The The stars behind are red shifted. This is relativistic beaming, the compression of light in the direction of our motion. The tidal forces are strengthening. 300,000 kilometers. We're falling at perhaps a few % of the speed of light now. The neutron star ahead dominates our field of view, a brilliant point growing larger with each passing second. The surface is too small to resolve details yet, but we can see that it's bright, hot, radiating enormous amounts of energy into space, and we can feel it now. The tidal forces have grown strong enough to be noticeable. Our feet are being pulled harder than our head, not by much, but enough that if we were conscious, if we were somehow surviving this impossible scenario, we would start to feel a stretching sensation, like being on a medieval rack, gentle at first, just a slight tension, a feeling that something is pulling at the extremities of our body. This is the beginning of spaghettification, the poetic term for tidal disruption, the process by which gravitational gradients tear objects apart by pulling harder on the near side than the far side. It's one of the most fundamental consequences of gravity acting across extended objects, a manifestation of the fact that gravity weakens with distance, creating differential forces across anything with spatial extent. It happens everywhere gravity varies across space. It happens to galaxies approaching supermassive black holes, their spiral arms stretched and torn by tidal forces until they form long streams of stars. It happens to stars that wander too close to galactic centers, ripped apart in spectacular tidal disruption events that create enormous flares of radiation. It happens to comets that pass too near the Sun. Comet Shoemaker, Levy 9 famously broke into more than 20 fragments before impacting Jupiter in 1994, torn apart by Jupiter's gravity. And it's about to happen to us in a much more extreme fashion. The physics is straightforward, but the consequences are profound. Gravity follows an inverse, square law. Double your distance from a massive object, and the gravitational force drops to 1/4. This means that if your feet are closer to a neutron star than your head, they experience stronger gravity. In normal circumstances, on Earth, this difference is negligible, a few parts per billion across the height of a human body. But near a neutron star, where gravity is millions of times stronger and varies over much steeper gradients, the difference becomes catastrophic. The tidal force, the stretching force created by this gravity gradient, scales with both the mass of the object creating it and inversely with the cube of the distance. This cubic dependence means tidal forces grow rapidly as you approach. At twice the distance, the tidal force is 1/8 as strong. At half the distance, it's 8 times stronger. This exponential growth is why tidal effects near neutron stars and black holes are so devastating. 200,000 kilometers from the surface, about half the distance from Earth to the Moon. And the stretching is getting worse by the second. We're being pulled longer, stretched in the radial direction, the line pointing toward the neutron star's center. The acceleration at our feet exceeds the acceleration at our head by perhaps 10 times Earth's gravity now. Our spine is being extended, vertebrae pulled apart, the soft tissues compressed and elongated simultaneously. At the same time, we're being compressed from the sides, squeezed inward horizontally. This compression is equally fundamental to spaghettification, but often forgotten in popular descriptions. It exists because gravitational field lines converge toward the center of mass. Our left side is being pulled slightly toward the right, toward the direct line between us and the neutron star. Our right side is being pulled slightly toward the left. The same principle applies front to back. The result is a 3-dimensional stress field: stretch vertically, compress horizontally. This is the geometric signature of tidal forces, the pattern that defines how gravity tears things apart when it varies too rapidly across space. stretch in one direction, squeeze in another. This is the recipe for spaghettification, and we're still relatively far from the star's surface, still hundreds of thousands of kilometers from actual impact. The forces will only grow worse, much worse, as the fall continues. 100,000 kilometers. The fall continues, relentless, accelerating. We're falling faster than escape velocity from Earth now, faster than any spacecraft we've ever built. Our velocity has climbed past 15 kilometers per second, 2025. The neutron star fills our forward view, a sphere of impossible density, growing larger by the second, rotating beneath us if it's a pulsar, sweeping its beams across space with clockwork precision. If we could still see in the normal sense, the view would be spectacular and terrible. The star itself glows in X-rays and ultraviolet, its surface temperature in the millions of Kelvin, making it shine with a harsh blue, white light. If there's an accretion disk, matter from a companion star spiraling inward, it would be visible as a bright, flattened structure, glowing even more intensely than the star itself, heated to millions of degrees by friction and compression. But visual observation is becoming difficult. The velocity is so high now that Doppler shifting is severe. Light from ahead appears blue, shifted to higher energies. Light from behind, if we could look back, would be red, shifted. The universe is taking on a distorted appearance, compressed forward, dimmed backward, painted in colors no human eye was designed to see. The magnetic field is strong now, very strong. If we had iron in our blood, which we do, bound within hemoglobin molecules, essential for oxygen transport, the magnetic field would be trying to align those iron atoms with its field lines. The effect is still small at this distance relative to the other forces at play. But it's there, present and growing. The field is perhaps 1 million Gauss here, about 1 million times stronger than Earth's magnetic field, strong enough to interfere with electronic equipment, if any still functioned, strong enough to create sensations in biological tissue, if any nerves still operated to feel them. For reference, a refrigerator magnet is about 100 Gauss. A strong laboratory magnet might reach 100,000 Gauss. We're beyond the realm of laboratory physics now, into field strengths that only exist near neutron stars, magnetars, and the most extreme astrophysical environments. The tidal forces are overwhelming now. The stretch has gone from uncomfortable to painful to devastating to beyond any biological reference point. The difference in gravitational pull between head and feet is now dozens of times Earth's gravity. Our molecular bonds, the electromagnetic forces that hold our atoms together in meaningful arrangements, are being tested against purely gravitational forces. At the cellular level, disaster has spread throughout what remains of biological organization. Cells are being deformed, stretched lengthwise, compressed from the sides into elongated ellipsoids. Cell membranes, those delicate lipid bilayers that separate inside from outside, are rupturing. The carefully maintained ionic gradients that allow nerves to fire and muscles to contract are collapsing. Proteins are unfolding. They're three-dimensional structures, carefully folded chains of amino acids that took millions of years of evolution to optimize, are being straightened out by forces they have no defense against. DNA helices are being stretched, the hydrogen bonds between base pairs straining and snapping, the complex machinery of biology, ribosomes, mitochondria, the elegant molecular motors that drive cellular processes, is being torn apart by the sheer difference in gravitational acceleration across the small distances that separate cellular organelles. But there's no time to experience this at a conscious level. No time for pain to register, for the nervous system to process what's happening. Everything is happening far too fast for biological response times. We fall in a state beyond sensation, beyond consciousness. beyond life as any definition would recognize it. 50,000 kilometers. We're falling at a significant fraction of light speed now. Time dilation has become severe. For every second that passes for us, several seconds pass for distant observers. We're moving through time differently than the rest of the universe, our personal timeline diverging from the cosmic clock. The neutron star is massive in our view now, no longer a distant point or even a sphere, but a wall of radiation and gravity ahead of us, dominating our entire forward field of view. If any consciousness remained, any capacity for perception, we would see it approaching, not with the gentle growth of a distant object, but with the rushing immediacy of imminent collision. And the tidal forces are catastrophic. The stretching has exceeded the tensile strength of any biological material by orders of magnitude. If we were somehow still intact, somehow still a cohesive object, we would be elongating rapidly, pulled into a long strand like pulled taffy, like molten glass being drawn into fiber, like the spaghetti that gave this process its name. But we're not intact. We haven't been intact for many seconds now. We're breaking apart. First at the cellular level, and that was thousands of kilometers ago. Then at the molecular level, the larger organic molecules succumbing to the gradient forces, breaking their bonds, separating into smaller and smaller pieces. The bonds that hold complex molecules together. The hydrogen bonds that stabilize proteins and DNA. The covalent bonds that link carbon atoms into organic chains. Even some of the stronger ionic bonds between charged atoms are being tested against forces they were never designed to withstand. Forces that have nothing to do with chemistry and everything to do with the geometry of curved space-time. And they're failing. One by one, then in cascades, the bonds snap. Long chain polymers break into shorter chains. Proteins fragment into individual amino acids. Nucleotides separate from the sugar, phosphate backbone of DNA. The elegant molecular architectures that took billions of years of evolution to develop disassemble in microseconds, reduced to their chemical components, then to simpler molecules, then to individual atoms. 20,000 kilometers from the surface now. The descent is accelerating beyond imagination, beyond the possibility of human comprehension. We're falling at perhaps 20% of light speed, maybe more. 60,000 kilometers per second, fast enough to cross the diameter of Earth in a fifth of a second. The kinetic energy involved is staggering. Even individual atoms carry energies comparable to particles in high-energy physics experiments. Energies measured in electron, volts and giga, electron, volts rather than the thermal energies of normal chemistry. The relativistic effects are severe and growing more pronounced with each passing fraction of a second. The universe ahead of us is blue, shifted dramatically. Photons traveling toward us gain energy in our reference frame, their wavelengths compressed by our velocity. The radiation from the neutron star is compressed to higher and higher energies. X-rays become gamma rays. Visible light, if any remained visible, becomes hard ultraviolet, then soft X-rays. The electromagnetic spectrum marches steadily toward higher frequencies, toward more energetic photons. The neutron star itself, already a fierce source of X-rays from its million-degree surface, appears to blaze with gamma radiation in our reference frame, a furnace of high-energy photons that would ionize any remaining molecular bonds, strip electrons from atoms, reduce complex chemistry to simple physics. The magnetic field here is 1 billion Gauss or more, depending on the type of neutron star we're approaching. For a normal pulsar, it might be 1 or 2 billion Gauss. For a magnetar, a neutron star with an especially powerful magnetic field, it could reach 1,000 billion Gauss or more, a quadrillion times stronger than Earth's field. This is strong enough to do something remarkable and strange. It starts to affect quantum mechanics itself, in normal physics on Earth. Electrons orbit atomic nuclei in shapes defined by quantum mechanical wave functions. For hydrogen, the simplest atom, just one proton and one electron, the ground state is spherical, a probability cloud surrounding the nucleus with no preferred direction. For more complex atoms, the orbitals take on more complex shapes: dumbbell-shaped p orbitals, cloverleaf-shaped d orbitals, and so on, but all maintain rough symmetry. But in magnetic fields this strong, those orbitals deform dramatically. The magnetic field energy exceeds the binding energy of atomic electrons. Instead of spherical clouds, the electron probability distributions elongate into thin cylinders aligned with the magnetic field. Hydrogen atoms, that most fundamental and abundant element, get squeezed into elongated shapes, stretched along the magnetic field lines until they're perhaps 200 times longer than they are wide, more like needles than spheres. More complex atoms fare even worse. Carbon, nitrogen, oxygen, the building blocks of organic chemistry, all deform into anisotropic shapes, their electron clouds compressed perpendicular to the field and extended parallel to it. The periodic table, as we know it, ceases to apply. Chemical bonding follows different rules. Molecules that would be stable in normal space can't form, while structures that would be impossible on Earth become favored. The very structure of matter is being rewritten by the magnetic field, forced into configurations that don't exist anywhere else in the universe except near neutron stars and perhaps black holes. 10,000 kilometers from the surface, there's nowhere anymore in any meaningful sense, no intact body, no organized structure, no hierarchy of organization from atoms to molecules to cells to tissues to organs to organism. What was once a human being, a conscious, thinking entity with memories and hopes and fears, is now a stream of disrupted matter, a filament of atoms and ions and molecular fragments, stretched into a long thread by tidal forces, pointed at the neutron star like an arrow aimed at an inevitable target. Individual atoms, mostly hydrogen and oxygen from water molecules, carbon and nitrogen from proteins, calcium from bones, iron from blood, all the elements that composed a living thing now separated, ionized, streaming independently. Some may still be bound in small molecular groups. A water molecule here, a methane molecule there. But the complex structures are gone, broken down to their simplest components. The stream is still falling, still accelerating. Each atom, each ion follows its own trajectory, tracing geodesics through the curved space-time, falling faster and faster toward the dense surface below. The stream has width, perhaps tens of meters across by now, a thin filament by astronomical standards, but containing trillions upon trillions of particles, each one following a slightly different path, slightly different velocity, creating a diffuse strand of matter. If we could observe this from outside, from a safe distance, we would see a faint line of glowing plasma stretched vertically toward the neutron star, gradually brightening as it falls and heats, eventually impacting the surface in a brief flash of energy. But we can't observe from outside. We are the stream, or rather, the stream is all that remains of what we were. 5,000 kilometers. The velocity approaches 30% of light speed. Time dilation is extreme now. For every second that passes in the stream of matter that was once us, 4 or 5 seconds pass in the outside universe. Our timeline has slowed to a crawl relative to distant observers, stretched thin by the intensity of the gravitational field. The temperature is rising too. As we fall faster and faster, the few remaining gas molecules in the space around the neutron star begin to impact us from our perspective like a headwind. This isn't air. Space is still a near vacuum. But the relative motion is so high that even the scattered particles we encounter transfer enormous kinetic energy. Heating begins. The stream of matter glows, not from its own light, but from the friction of its passage through even the tenuous material near the neutron star. 2,000 kilometers. The magnetic field is measured in trillions of Gauss now, if this is a magnetar. The vacuum itself is polarized. Photons traveling through this region split in two, their quantum states affected by the intense magnetic energy density. Light behaves differently here than anywhere else in the universe. The neutron star's surface is visible now as an actual surface, not just a point of light. It's smooth, almost perfectly so. Any irregularities have been pulled flat by gravity. The crust is crystalline, a solid lattice of nuclei crushed to densities 1,000,000 times greater than steel, and it's rushing toward us. 1,000 kilometers. The last 1,000 kilometers. We're falling at perhaps 40% of light speed now. The kinetic energy is staggering. Each atom in the stream carries as much energy as it would from nuclear fusion, just from the velocity of its fall. The time dilation is extreme. For every second that passes for us, 10 seconds pass for distant observers. We're moving through time at 1/10 the rate of the outside universe. And the heating is becoming catastrophic, even in the near vacuum of space near the neutron star. The relative velocity is so high that impacts with stray particles release enormous amounts of energy. The stream of matter begins to glow white, hot, then blue-hot, radiating away energy even as it continues to fall. 500 kilometers. The surface is right there, a wall of impossible density, spinning beneath us at a significant fraction of light speed. If this neutron star rotates hundreds of times per second, its equatorial surface is moving at perhaps 20% of light speed or more. We're not going to land so much as collide with a surface moving at relativistic velocities. 200 kilometers, 100 kilometers, 50 kilometers. The final descent is measured in fractions of seconds by any clock. We're falling at nearly half the speed of light. The kinetic energy in each atom is staggering. The time dilation means we're experiencing time at perhaps 1/20th the rate of the outside universe. And then, impact. What hits the neutron star's surface is no longer recognizable as human. It's a stream of atoms and fragments, elongated by tidal forces, compressed from the sides, moving at approximately half the speed of light. The kinetic energy in this stream is comparable to that released by nuclear weapons. Not because of any nuclear reaction, but simply from the velocity of the fall. When this stream hits the solid crust, several things happen simultaneously. First, there's the sheer mechanical shock of the impact. The atoms strike the surface and stop, or rather, they're decelerated over a distance measured in fractions of millimeters, brought from half-light speed to zero in an absurdly short time. The deceleration is measured in millions of g-forces, millions of times Earth's gravity, numbers that strain comprehension. Every chemical bond that somehow survived the fall is broken instantly. Every molecular structure is shattered. The atoms themselves, the nuclei and their electrons, are disrupted by the violence of the impact. The kinetic energy is converted to heat, enormous amounts of heat. The impact point on the neutron star's surface flashes white hot, then blue hot, then into frequencies beyond visible light. X-rays flood the region. For a brief moment, measured in microseconds, the impact site becomes as hot as the core of a normal star, perhaps hotter. But the neutron star is massive. The energy released by our impact, enormous as it is nothing compared to the star's total heat content. The hotspot cools almost immediately, radiating its energy away into space or conducting it down into the crust below. Second, there's the integration. The atoms that made up our body, the carbon, the oxygen, the nitrogen, the trace elements, don't just sit on the surface. They can't. The gravity is too intense. Within moments, they're pulled down, pressed into the crust, compressed by the overwhelming weight of the gravitational field. The pressure at the surface is measured in millions of billions of pascals. This is enough to alter atomic structure. Electrons are pushed closer to nuclei. Atomic radii shrink. The matter becomes denser, more compact, taking on properties that don't exist anywhere else in the universe. As the atoms sink deeper, if they could sink at all against the solid crust, they would encounter even more extreme conditions. The inner layers of the crust are a bizarre state called nuclear pasta, where atomic nuclei deform under pressure into shapes like cylinders, slabs, tubes, and spheres again, forming structures that resemble various types of pasta at the quantum level. Below that, in the outer core, free neutrons flow like a superfluid, a quantum liquid with zero viscosity. Below that, in the inner core, physics becomes speculative, perhaps quarks, perhaps strange matter, perhaps something we haven't even theorized yet. Third, there's the relativistic consideration. From the perspective of a distant observer, our impact happened in slow motion. Time dilation means they saw us approach the surface gradually, taking longer and longer to cover the last few kilometers. When we finally hit, from their perspective, it looked like we were moving through molasses, our motion slowed by the warping of space-time near the dense surface. But from our perspective, from the perspective of the atoms in the stream, everything happened in normal time, fast, brutal, instantaneous. This asymmetry is a consequence of general relativity. Time flows differently at different depths in a gravitational field. The stronger the field, the slower the time. Near the surface of a neutron star, time runs at perhaps 1/10 the speed it does far from any massive object. This means something strange. If there were two streams of matter falling toward the neutron star from different distances, and they both hit at what appears to be the same moment from far away, they would actually experience different amounts of proper time during their falls. The one that started farther away would age more during the descent, even though they arrived simultaneously from an external observer's perspective. Fourth, there's the electromagnetic contribution. If the neutron star has a strong magnetic field, and most do, the charged particles in our disrupted atoms would be affected. Protons and electrons would spiral along magnetic field lines, radiating energy as they spiral. This is called synchrotron radiation, and it adds to the spectacular light show of the impact. The magnetic field might also channel the incoming matter, directing it toward the magnetic poles, rather than letting it impact randomly across the surface. This is what happens in accreting neutron stars. Stars that are pulling matter from a companion star in a binary system. The material follows magnetic field lines down to the poles, creating hotspots that emit X-rays. Finally, there's the quantum mechanical consideration. At the scale of individual atoms impacting a surface this extreme, quantum effects become important. The exact quantum state of each electron matters. The Pauli exclusion principle, which prevents fermions like electrons and neutrons from occupying identical quantum states, determines how the atoms integrate into the crustal lattice or are rejected from it. In some sense, the atoms that were once us become part of the neutron star, not in any meaningful way, not in any way that preserves identity or structure or even chemical composition. The carbon that made up our cells might be compressed so thoroughly that it's indistinguishable from iron at the same density. The atomic structure is forced into configurations determined entirely by pressure, gravity, and quantum mechanics. But the mass is there. The neutron star is heavier by exactly the amount we weighed, plus the kinetic energy of our fall converted to mass energy through Epp-Mersenne. The total mass energy is conserved, integrated into the star, distributed across its enormous bulk, and the neutron star continues spinning, continues rotating hundreds of times per second, if it's a pulsar, continues generating its enormous magnetic field, if it's a magnetar, continues existing as the densest stable matter in the universe, balanced on the knife edge between neutron degeneracy pressure and gravitational collapse, completely unchanged by our arrival, unaffected by our sacrifice, patient and eternal in the way that cosmic objects can be patient and eternal. Let's step back from the visceral reality of the fall and contemplate what made it impossible. Not just unlikely, not just dangerous, impossible, even with perfect shielding, even with materials stronger than anything we know, even with some theoretical protection against every force and field we encountered. A human being could not survive the approach to a neutron star. The reasons are fundamental, rooted in the very nature of matter and gravity and space-time. Consider the tidal forces first. These aren't forces in the usual sense. They're gradients, differences in force across distance, and they scale differently than regular forces do. If you double the strength of a uniform gravitational field, you double the force on an object. That's manageable, at least in principle. We could imagine engineering solutions, stronger materials, better designs. But tidal forces scale with the gradient, which means they increase much faster as you approach a dense object. The closer you get, the more rapidly they grow. And because neutron stars are so small and so massive, the gradient becomes steep very quickly. At a certain distance, called the tidal disruption radius, the tidal force exceeds the material strength of any object. For neutron stars, this radius is typically tens of thousands of kilometers from the surface, maybe more depending on the star's mass and the object's composition. A human body would reach this radius long before reaching the surface. And there's no engineering solution. You could encase the body in diamond. You could use carbon nanotubes. You could invoke some hypothetical material stronger than anything we know. It wouldn't matter. The tidal force doesn't respect material strength. It reaches through everything, pulling on each individual atom, based on its distance from the neutron star. The only way to avoid tidal disruption would be to make the object smaller, to reduce the distance across, which the tidal gradient acts. But then you'd have to fit a conscious being into something tiny. And eventually, you'd reach the scale of atoms, and tidal forces would start pulling apart atomic structure itself. There's no winning this game. Then consider the magnetic field in all its extraordinary strength. In fields of 1 trillion Gauss or more, typical for young neutron stars, atoms deform dramatically. Hydrogen becomes cylindrical, stretched to perhaps 200 times longer than it is wide. Carbon atoms, nitrogen, oxygen, all the elements essential to organic chemistry, suffer even more severe distortion. Their electron clouds warped into shapes that have no analog in terrestrial chemistry. This isn't a superficial effect that might be compensated for somehow. It's a fundamental alteration of atomic structure, changing the shapes of electron orbitals, modifying the energy levels of atomic states, altering how atoms bond to each other. In these fields, chemistry itself becomes different. Molecules that are stable on Earth may be unable to form. Bonds that are strong in normal magnetic environments may weaken or change character entirely. Life as we know it depends completely and fundamentally on chemistry, on the ability of atoms to form complex, stable molecules with specific three-dimensional structures, on proteins folding into precise shapes that determine their function, on DNA maintaining its double helix structure, with base pairs aligned properly to encode genetic information, on cell membranes preserving their integrity as barriers between internal and external environments, on the specific binding of enzymes to substrates, of signaling molecules to receptors, of transcription factors to DNA. All of this chemistry requires atoms to behave as they do in normal magnetic fields. The precise shapes of molecules matter. The exact angles of chemical bonds matter. The specific energies of electronic transitions matter. In a magnetic field strong enough to deform atomic structure by factors of hundreds, none of this is possible. The delicate architecture of biochemistry collapses. Proteins can't fold properly because the amino acids that compose them have different shapes. DNA can't maintain its structure because the nucleotides are distorted. Cell membranes can't form because the lipid molecules are elongated into shapes that don't pack together properly. The chemistry of life simply cannot function in these environments. You're not just being killed. The very possibility of being alive is being erased at the molecular level. You could try to shield against the magnetic field, to create a field-free region where normal chemistry could persist. Magnetic shielding works by redirecting field lines around the protected region using materials with high magnetic permeability, materials that absorb magnetic field and rotate through themselves rather than letting it pass through. This is how we shield sensitive instruments on Earth from stray magnetic fields. But near a neutron star, the field is so strong that it would saturate any shield almost immediately. Magnetic materials can only absorb field up to their saturation point, the point where all their magnetic domains are aligned, and they can't accept any more field. Beyond that, field lines are forced through the material regardless of its composition. A trillion Gauss field would saturate any known material within micrometers. You'd need shield thickness measured in meters just to achieve modest reduction in field strength. And even then, the field at the center might still be thousands or millions of Gauss. Far more than enough to disrupt biochemistry. And the fundamental problem remains: the magnetic field reaches through everything. It's not blocked by matter the way light can be blocked. It permeates all of space with only slight modification by material properties. There's nowhere to hide from it, no shelter that can be constructed, no barrier that can be raised. Then there's the radiation environment, brutal beyond description. Neutron stars emit X-rays, copious amounts of X-rays. Young pulsars can radiate the equivalent of 10,000 suns worth of power, much of it in high-energy electromagnetic radiation. Some of this comes from the star's thermal emission. Million-degree surfaces naturally radiate in the X-ray range. But much comes from the pulsar mechanism itself, from charged particles accelerated to relativistic speeds in the magnetosphere, spiraling along field lines and radiating synchrotron emission as they spiral. X-rays damage living tissue by ionizing atoms, breaking chemical bonds, creating free radicals, highly reactive molecules that cascade through cells, causing widespread damage. Even small doses accumulate over time, increasing cancer risk, damaging DNA, potentially killing cells directly if the dose is high enough. Near a neutron star, the dose wouldn't be measured in millisieverts, the units used for medical X-rays, or even sieverts, the units used to describe lethal radiation doses from nuclear accidents. The dose would be measured in some absurdly high number that would cook biological tissue instantly, depositing so much energy so quickly that heating alone would be fatal, never mind the chemical damage from ionization. At a distance of a few thousand kilometers from an actively emitting pulsar, the radiation flux might be equivalent to standing at ground zero of a nuclear weapon detonation, but sustained, continuous, unending. The X-ray photons would penetrate tissue, depositing their energy, breaking molecules apart, converting the ordered chemistry of life into a hot, ionized plasma of disconnected atoms. You could try to shield against this radiation too, and in principle X-ray shielding is feasible. X-rays can be absorbed by dense materials, lead, tungsten, tantalum, materials with lots of electrons that can interact with high-energy photons. A meter of lead can stop most medical X-rays. A few meters can stop much harder X-rays. But near a neutron star, you'd need extraordinary amounts of shielding. Meters of lead, certainly, perhaps tens of meters, maybe more, depending on how close you wanted to get and how long you wanted to survive. The shielding would need to surround you completely, protecting from all angles, because the radiation comes from all directions near a neutron star, reflected off any nearby matter, scattered by the magnetic field, emerging from the star's surface in all directions. That's theoretically feasible for a spacecraft, perhaps. A massive, heavily armored vessel with meters, thick walls of tungsten or depleted uranium, designed purely for protection rather than efficiency. But the mass of such shielding would make the tidal problem dramatically worse, because tidal forces depend on the size of the object being torn apart. A larger, heavier craft experiences greater tidal stress than a small, light one, because the force gradient acts across a larger distance. There's a fundamental trade-off with no good solution: shield against radiation, and you make yourself more vulnerable to tidal forces. Minimize your size to reduce tidal stress, and you can't carry enough shielding to protect against radiation. You can't win both battles simultaneously. And we haven't even mentioned the gamma rays yet. Many neutron stars, especially magnetars during their active periods, emit gamma rays. Photons with energies measured in millions of electron volts. These are even harder to shield against than X-rays, requiring even thicker barriers, even more mass, even worse tidal problems. And then there's the velocity issue. By the time any falling object reaches the neutron star's surface, it's moving at a substantial fraction of light speed. 30%, 40%, maybe even 50%, depending on the starting distance and the star's mass. The kinetic energy at this velocity is staggering. If a 1 kilogram object hit the surface at half light speed, the kinetic energy would be approximately 1.1 times 10 to the 17th joules. That's about 26 megatons of TNT equivalent, about the energy of a large thermonuclear weapon, from a 1 kilogram mass. Simply from the velocity of the fall, there's no way to slow down gradually, no way to decelerate safely. The escape velocity from the neutron star's surface is about half the speed of light, which means you'd need to shed that much velocity to avoid impact. And shedding that velocity requires energy. Enormous amounts of energy, far beyond what any conceivable rocket could provide. You could try aerobraking, using atmospheric friction to slow down, but neutron stars don't have atmospheres, not in the traditional sense. The atmosphere is perhaps a few micrometers thick at most, and it's not gas. It's a plasma of ions and electrons, held impossibly close to the surface by gravity. There's nowhere to brake, no way to slow. The impact is inevitable, and it's always at relativistic velocities. Finally, there's the time dilation. From the perspective of someone falling toward a neutron star, the universe speeds up around them. What takes 1 second for them might take 10 seconds for distant observers. This means they age less during the fall than the outside universe does. This isn't just a curiosity, it has practical implications. If you somehow survived the fall and wanted to communicate with the outside world, your messages would be time dilated. They would arrive at a slower rate than you sent them. Red, shifted to lower frequencies, stretched out in time. And messages from the outside world would arrive blue, shifted, compressed in time, carrying more information per your time second than they were meant to contain. This would make any kind of rescue operation extraordinarily difficult to coordinate. The physics conspires against survival at every level. Tidal forces tear you apart. Magnetic fields disrupt atomic structure. Radiation cooks you from the outside in. Velocity ensures that impact is always catastrophic. Time dilation means you can't coordinate with helpers, and all of these effects grow stronger and stronger the closer you get. There's no engineering around them, no clever solution, no hypothetical technology that could save you. The fall toward a neutron star is not just dangerous in the way that climbing Everest is dangerous, where proper preparation and equipment and luck might see you through. It's impossible in the way that traveling faster than light is impossible, where the laws of physics themselves say no, where the universe draws a line and says, beyond this point, your biology, your chemistry, your very atomic structure cannot exist as you know it. The fall is a one-way journey into conditions that are not compatible with complexity, with organization, with life. And yet it's beautiful, isn't it? The fact that such extremes exist. The fact that the universe contains places where matter is compressed to nuclear densities, where magnetic fields reshape atoms, where gravity becomes so intense that time itself flows differently. These neutron stars are laboratories of extreme physics, natural experiments that test our theories at conditions we could never replicate artificially. Every observation we make of them, every pulsar timing measurement, every X-ray spectrum, every gravitational wave detection from merging neutron stars, teaches us something about how matter behaves at its limits, about how space-time responds to extreme curvature, about the fundamental laws that govern reality. We can't survive near them, but we can study them from afar. We can wonder at them. We can let our minds approach what our bodies never could, exploring through mathematics and physics and imagination what direct experience must forever be denied. Not all neutron stars are created equal. The experience of falling would vary depending on which type of neutron star we chose, which specific example among the thousands we've discovered. Consider a magnetar, for instance. These are the most magnetic objects in the universe, with field strengths reaching a quadrillion Gauss or more. That's 1,000 times stronger than a typical neutron star's field, and a quadrillion times stronger than Earth's. In a magnetar's field, bizarre things happen to the vacuum of space itself. Quantum electrodynamics predicts that in sufficiently strong magnetic fields, the vacuum becomes birefringent. It refracts light differently depending on polarization, like a calcite crystal. Photons traveling through this region can spontaneously split into electron-positron pairs, which then recombine, creating a peculiar interaction between light and magnetism. The field is so strong that it warps atoms into extreme needle-like shapes, hundreds of times longer than they are wide. Atomic orbitals become so distorted that chemical bonding becomes virtually impossible. Complex molecules simply cannot form, and the field itself carries so much energy that it can crack the neutron star's crust, causing star quakes, sudden shifts in the crustal structure that release enormous amounts of energy in bursts of X-rays and gamma rays. Falling toward a magnetar would be even more catastrophic than falling toward a typical neutron star. If such a distinction is meaningful in this context of universal catastrophe, the magnetic forces would tear apart any biological structure earlier in the fall, and the radiation environment would be even more intense. Or consider a millisecond pulsar. These are neutron stars that have been spun up by accreting matter from a companion star, rotating hundreds of times per second. In extreme cases, over 700 rotations per second. At these rotation rates, the equatorial surface is moving at significant fractions of light speed, 25% or more, fast enough that relativistic effects become important, even at the surface itself. A millisecond pulsar's shape is noticeably oblate. It bulges at the equator due to centrifugal forces. The polar radius might be 10 kilometers, but the equatorial radius could be 11 or 12. This oblateness affects the gravitational field, making it slightly weaker at the equator than at the poles. Falling toward a millisecond pulsar's equator would mean encountering a surface moving at a quarter light speed perpendicular to our fall. The impact would be angled, tangential, perhaps even glancing. The kinetic energy would be even higher than for a non-rotating star, combining our infall velocity with the surface's rotational velocity. The result would be even more violent, if that's possible. Or consider an isolated neutron star, old and cold. Not all neutron stars are pulsars. Many don't have the right magnetic field orientation to beam radiation toward Earth. Others have slowed down so much that they no longer generate detectable pulses. These quiet neutron stars still exist, still spin as or beat slowly, still maintain their incredible density and gravity. They're just harder to detect. Falling toward an old, cold neutron star would be slightly different than falling toward a young, hot one. The surface temperature might be only a few 100,000 Kelvin instead of 1,000,000. The magnetic field might have decayed somewhat, dropping from 1,000,000,000 Gauss to tens or hundreds of billions. The tidal forces would be the same. Those depend only on mass and distance, not on the star's electromagnetic properties. But the radiation environment would be milder, the magnetic effects less extreme. Not that it matters. The fall would still be utterly fatal, just slightly less spectacularly so. Or consider a neutron star in a binary system, accreting matter from a companion. These systems are called X-ray binaries, and they're among the brightest X-ray sources in the sky. The neutron star pulls material from its companion, usually a normal star that has swollen large enough that its outer layers overflow the Roche lobe, the gravitational boundary beyond which material is pulled toward the compact object. This material doesn't fall straight down onto the neutron star. It has angular momentum from orbiting the companion, so it forms an accretion disk, a swirling disk of hot plasma spiraling inward, heating up from friction and compression, radiating enormous amounts of X-rays. The innermost edge of this disk hovers just above the neutron star's surface, perhaps a few kilometers up, held aloft by the fierce radiation pressure and magnetic fields. Falling towards such a system, we would first encounter the accretion disk. This alone would be fatal, of course. The disk material is heated to millions of Kelvin by friction and compression. It's dense enough and hot enough to vaporize anything that entered it. The radiation environment is even more intense than around an isolated neutron star, with the disk emitting as much power as thousands or millions of suns. But if we somehow passed through the disk, somehow survived its temperatures and densities and radiation, we would then encounter the neutron star itself, probably having been redirected by magnetic field lines to fall toward the magnetic poles, where the accreting material forms hot spots that emit intense X-rays. The physics of the final impact would be similar to before, but we'd arrive as part of a stream of accreting matter, funneled by magnetic forces, compressed and heated before we even reached the surface. Each type of neutron star offers its own flavor of impossible death. Each variation in mass, spin rate, magnetic field strength, age, binary status creates slightly different conditions, slightly different environments, slightly different sequences of destruction. But the end result is always the same: total disintegration, complete obliteration of structure at every level from the macroscopic down to the atomic. Integration into the neutron star's mass, becoming part of the densest stable matter in the universe. Let's pull back now, in these last moments before sleep takes you. Pull back from the horror of the fall, from the violence of the forces, from the impossible physics of neutron star environments. Let's contemplate what this means. Neutron stars exist. Right now, in our galaxy alone, there are perhaps 1 billion of them. Most are invisible to us, dark and quiet, slowly cooling in the depths of space. But they're there, scattered through the Milky Way, remnants of stars that died long before the sun was born. Some are pulsars, visible to us through their radiation, clocks of extraordinary precision marking time with each rotation. Some are magnetars, occasionally flaring with bursts of X rays and gamma rays, as their crustal structure adjusts to the decay of their enormous magnetic fields. Some are accreting matter from companions, lighting up the X-ray sky, spinning faster and faster as angular momentum transfers from the infalling material. And some are simply there, dark and dense, waiting in silence. Each one represents an extreme endpoint of stellar evolution. Each one is a massive star that ran out of fuel, collapsed, exploded, and left behind a core so dense that atoms cease to exist as we know them. These objects shouldn't exist. According to our everyday intuition, matter shouldn't be able to pack itself so tightly. Gravity shouldn't be able to overcome the electromagnetic forces and quantum pressures that usually keep atoms apart. Time shouldn't be able to flow at different rates depending on where you are. And yet they do exist. The universe contains them. Reality includes neutron stars as part of its repertoire of possible objects, alongside planets and normal stars and black holes and galaxies and all the other structures that populate the cosmos. And that tells us something profound about the universe itself. It tells us that the range of possible physical conditions is wider than we experience in our daily lives. Much wider. The comfortable middle ground we inhabit on Earth, where water is liquid, where electromagnetic forces are the strongest thing we encounter, where gravity is gentle enough to be overcome by muscle power. This is a tiny corner of possibility space. Most of the universe is more extreme. The space between stars is colder than we can easily achieve in laboratories. The cores of stars are hotter than anything on Earth. The densities in neutron stars exceed anything we could produce artificially. And life, complex and organized and fragile, exists only in the narrow band of conditions where chemistry can function, where molecules can form and persist, where information can be stored in biological structures. We are, in a very real sense, edge cases, unusual configurations of matter that happen to be possible in the specific conditions that prevail in planetary atmospheres, in the thin layer of air clinging to worlds like Earth. Most of the universe is not hospitable to us. Most of the universe would destroy us instantly if we encountered it unprotected. And yet here we are, thinking, wondering, contemplating our own impossibility. We are made of atoms forged in stars, scattered by supernovae, reassembled on a planet orbiting a later generation star, organized by evolution into patterns capable of self-awareness. We can think about neutron stars, even though we could never survive near one. We can understand the physics that would destroy us. We can mathematize the forces, calculate the gradients, predict what would happen at each stage of the fall. This ability to know what we cannot experience, to understand what we cannot survive, to imagine what lies forever beyond our reach. This might be the most remarkable thing about consciousness. We transcend our limitations through thought. We approach the unapproachable through mathematics. We touch the untouchable through imagination. And so tonight, we've fallen toward a neutron star together. Not really, of course. We're safe here, breathing slowly, lying comfortably, far from any extreme gravitational field. But in imagination, in the theater of the mind, we've made the journey. We've felt the acceleration build, experienced the tidal forces grow, witnessed the destruction of structure at every level from the biological down to the atomic. We've seen what happens at the limits of physics, where gravity becomes so strong that time itself bends, where magnetic fields reshape atoms, where kinetic energy rivals nuclear explosions. And now, having seen it, having contemplated it, we can let it go. Let the images fade. Let the physics equations blur. Let the velocity numbers and field strengths and density measurements drift away like clouds dispersing in a gentle wind. Your breathing has slowed during this journey. Your heart rate has settled into its resting rhythm. The muscles in your face have softened. The tension in your shoulders has released. The thoughts that were racing when we began have quieted to a gentle murmur. This is as it should be. You've traveled far tonight, through fields of impossible force, past gradients that tear matter apart, into regions where time flows differently and atoms deform under magnetic stress. But you've returned safely. You're here, in your comfortable space, in your soft bed, in the gentle gravity of Earth, where chemistry functions normally and molecules hold their shapes and consciousness, can persist long enough to contemplate its own existence. Let yourself appreciate this gift, the gift of existing in conditions where existence is possible, the gift of living in a universe that contains both the gentle and the extreme, both the habitable and the impossible, both the familiar and the strange. You are a pattern in space-time, complex and temporary, organized and aware. You emerge from stardust, assembled by processes that took billions of years, shaped by evolution, imbued somehow with the capacity to wonder about the cosmos that made you. And one day, you'll return to dust, not to a neutron star, probably. The universe will find other ways to recycle your atoms. But return you will, eventually, contributing your matter and energy back to the great cosmic cycle of creation and destruction. Until then, you have this moment, this breath, this heartbeat, this quiet space where thoughts can wander through the cosmos while the body rests in peace. So breathe slowly. Let your eyes close fully if they haven't already. Feel the weight of your body against the bed, supported and safe. The neutron star spins on, far away in the deep night, patient and terrible and beautiful. It will still be there tomorrow, still spinning, still dense, still marking time with each rotation. But you don't need to think about it anymore tonight. You've paid your visit to the extreme. You've contemplated the impossible. You've wondered at the limits of physics and survived the journey in imagination. Now it's time to simply rest, to let the thoughts dissolve, to sink into the darkness that waits behind your closed eyes, warm and welcoming and soft. Sleep comes like a gentle fall, but without acceleration, without velocity, without tidal forces. Just a slow descent into rest, natural and needed and kind. The universe continues its dance, stars spinning, galaxies turning, neutron stars marking time. But you're allowed to stop watching for a while, to close the observatory, to extinguish the mental lights, to drift. Among the stardust from which you came, among the thoughts that brought you here, among the infinite possibilities of a universe vast enough to contain both you and neutron stars, both consciousness and crushing gravity, both the fragile and the eternal. Rest now. The journey is complete. The fall has ended not in destruction but in understanding, and understanding is its own kind of peace. Sleep softly, traveler. The stars will keep their watch. The neutron stars will continue their impossible existence. And you, made of atoms forged in ancient suns, will rest. Will dream perhaps. Will wake tomorrow to contemplate other wonders. But for now, simply sleep. Among the stardust. Among the silence. Among the ancient light that has traveled so far to reach this moment. Good night.